Hello students, welcome to online classes. In the previous class, we have learned Euclid division lemma and the problems related to Euclid division lemma and also finding HCF using Euclid division lemma. In this session, we are going to learn fundamental theorem of arithmetic and prime factorization method, LCM and HCF by prime factorization method, and also rational and irrational numbers. Before going to this, let us see and let us recall the numbers which we have learned in the previous classes. The first numbers is prime numbers, composite numbers, rational numbers and irrational numbers. Among these numbers, first let us see what is the prime numbers. Students, what is the prime number? Yes, the number which has only one and itself has factors is called prime number. The number which has only one and itself has factors is called prime number. Yes, you are right. Now let us see the prime numbers between 1 and 100. So if you see, the numbers are starting from 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. So these are the important prime numbers. You should all remember the prime numbers from 1 to 100. From these prime numbers, 2 is the only even prime number. Remaining all numbers are odd numbers. So only 2 is the even prime number. And there are total 25 prime numbers between 1 and 100. Now what is a composite number? The number other than 1 which is not prime is called composite number. The number which is not prime is called composite number. Here we should not consider 1 because 1 is neither prime nor composite. Or else we can say the number which has more than 2 factors is called composite number. Yes, both are correct. Now let us see one note here. 1 is neither prime nor composite number. And also if you observe the numbers, natural numbers 1, 2, 3 up to so on, 1 is neither prime nor composite and 2 and 3 are prime numbers, then the 4 is the first composite number and the least composite number we can say as 4. And the composite numbers are starting from 4, 6, 8, 9, 10, 12, 14, 15 up to so on. These are all the composite numbers. Now let us see fundamental theorem of arithmetic. So before going to the fundamental theorem of arithmetic, do you recall what is Euclid's division lemma which we have studied in the previous class? Yes, given positive integers a and b, there exists a unique pair of integers q and r satisfying a is equal to bq plus r, where 0 less than or equal to r less than b. This is the Euclid division lemma which we have studied in the previous class. Then coming to question, if r is equal to 0 in the Euclid division lemma, the formula we are having a is equal to bq plus r. In that, if r is equal to 0, then what is the relationship between a comma b and q in a is equal to bq plus r? In solving this, let us take one example. 24 is equal to, I can write 8 into 3 plus 0. 24 is equal to 8 into 3, here remainder is equal to 0. So if remainder is 0, we can say 8 and 3 are factors of 24. Then we can conclude that if r is equal to 0, then a is divisible by b. Or else we can say if r is equal to 0, b and q are factors of a. One is, or we can say a is divisible by b, or b and q are factors of a. If you observe example, 24 is equal to 8 into 3, further if we factorize 2 into 4 into 3, 24 is equal to 2 into 2 into 2 into 3, 24, if we factorize 2 12s are 24, 2 6s are 12, 2 3s are 6 and 3 is a prime number, so we should stop the process. Then 2, 2, 2 and 3 are all are prime numbers. We can say, and the prime numbers should be in the ascending order. So always write prime numbers in ascending order, and this is the prime factorization of 24. What is the prime factorization of 24? 24 is equal to 2 into 2 into 2 into 3, or else you can write this as 2 cube into 3 power 1. Let us see one more example. Express 2020 as product of its prime factor. While solving this problem, let us take two methods. First is method 1 and method 2. In the method 1, first I am factorizing 2020 by taking as 2 and 1010 as factors. So 2020 I can factorize 2 and 1010, and 1010 further can be factorized as 2 and 505. Then 505 can be factorized as 5 and 101. Here if you observe 101 is a prime number, so stop process. So I can write 2020 is equal to, in the prime factorization, first prime number 2, next another prime number 2, and another prime factor 5, and the last prime factor 101. So I can write 2020 is equal to 2 into 2 into 5 into 101. So this is the one method where the 2 has been taken first. In the second method, if I am taking 5 as first, then 5 404 is a 2020. Then 404 further factorized, it can be written as 2 and 202. Then 202 can be written as 2 and 101. So 2020 is equal to, I can write 5 into 2 into 2 into 101. So 2020, if you observe, I can write in the two methods, 2 into 2 into 5 into 101 or 5 into 2 into 2 into 101. So if you observe here, we observe that same prime factors in both ways except only order. Thus the prime factorization of 2020 is unique except for the order in which the primes occur. So we can write 2 into 2 into 5 into 101 as in the power form, that is 2 square into 5 power 1 into 101, because 5 is coming only one time, so we are writing as 5 power 1, and 101 is also coming one time, so I am writing as 101 to the power of 1. So while writing prime factorization, always write in the power form. So this second one we have written 5 power 1 into 2 square into 101 to the power of 1. So both are same only except the order. This leads us to conjecture that every positive integer is either prime or it can be expressed as the product of primes in unique way. Now let us see the fundamental theorem of arithmetic. Every composite number can be expressed as a product of prime. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique except for the order in which the prime factors occur. That means every composite number can be expressed as a product of primes, only the difference is this factorization is unique except the order in which they occur. Note 1. Product of any two prime numbers is always composite number. So if we take example, 3 into 2 is equal to 6. Here 3 and 2 are prime numbers and the product 6 is a composite number. So we can say product of any two prime numbers is always composite number. So we can observe this, always prime into prime is composite number, that means product of two primes are always composite number. Prime into composite is also composite number. Composite into composite always composite number. So using this, let us see one example. The first problem is, how will you show that 17 into 11 into 2 plus 17 into 11 into 5 is a composite number. So this number is having two terms and we should show this is a composite number. Let us take same problem here. How will you show that 17 into 11 into 2 plus 17 into 11 into 5 is a composite number? Solution. Given number is the same number we have written here. If you observe two terms, 17 and 11 is a common in the both terms, so I can take 17 into 11 is common, then I can write 17 into 11. So in the first term 2 is left and in the second term 5 is left, so which I can write as 2 plus 5. So 17 into 11, 2 plus 5 I can write as 7. So 17 into 11 into 7, which can be written as 17 into 77. So if you observe these two numbers, this is a product of two numbers. So given number is a product of two numbers we got, so we can write this is a composite number, hence it is a composite number. Now let us see how to find LCM and HCF using prime factorization. LCM and HCF using prime factorization. Finding LCM and HCF using prime factorization, first step is, first write given numbers as a product of its prime factors along with powers. And in the step 2, to find LCM, list all prime factors once only, then the product of the greatest power of each prime factor is LCM. So first of all, what we need to do, to find LCM, list all prime factors, then the product of the greatest power of each prime factor, we will call it as a LCM. And step 3, to find HCF, list only common factors, then the product of the smallest power of each common prime factor is HCF. Students, if there is no common factor, what we need to do? So if there is no common prime number in prime factorization, then HCF of given number will be 1. Product of prime numbers, LCM and HCF. In LCM we should consider each and every prime, wherein in the HCF we should consider only common prime. And for after writing all the prime numbers, the greatest power I should consider, wherein for HCF I should consider smallest power. For least common multiple, take greatest power, and for highest common factor, take smallest power. Now let us see examples for finding LCM and HCF using prime factorization. Find the LCM and HCF of 72 and 108 by the prime factorization method. Solution: 72 factorized, 236 is 72, 2 18 is 36, 2 9 is 18, 3 3 is 9. So here 3 is a prime number, so we are stopping this process here, which we can write 72 is equal to 2 into 2 into 2 into 3 into 3, which can be written in the power form as 2 power 3 into 3 power 2. Now let us do second one. 108 prime factorization, 2 54s are 2, 27s are 54, and 3 9s are 27, 3 3s are 9. So here 3 is a prime, so stop process, which we can write as 108 is equal to 2 into 2 into 3 into 3 into 3. So which can be written in the power form as 2 square into 3 power 3. Now LCM. So if you observe two prime numbers, prime factorization, 2 in the first one and also in the second also 2, and 3 in the both. So there are total available prime numbers are 2 and 3. So we are listing all the prime numbers which are there in the 2 prime factorization, 2 into 3. Now coming to the powers. Which power to be taken now? In the second step, the powers we should consider for LCM, the highest power from this 2. There are 2 cube and 2 square. What is the highest power? Highest power is 3. So I should write 2 power as 3. And also compare 3 square and 3 cube. The highest power is 3. I should write 3 power as 3. So 2 cube is 8 and 3 cube is 27, which is 216. Now 216 is LCM. Now coming to the HCF. HCF is equal to, which we know that 2 into 3 I should take only common primes. So 2 and 3 are common in both prime factorization. So I am writing 2 and 3 here. Now coming to the power. The power we should take as the smallest powers. So in the prime factorization, 2 cube and 2 square, the smallest power is 2. So I should write 2 square, and for 3 also 3 square. So 2 square is 4, 3 square is 9, 4 into 9 is 36, 36 is HCF. So LCM is 216 and HCF is 36. Now here we will observe one thing. What is that? If we multiply given number 72 and 108, the product we are getting as 7776. And also we will multiply LCM and HCF, which is we are having 216 and 36. If we multiply, we are getting again 7776. That means both the cases we are getting same answer, 7776 is equal to 7776. So we can note here, what is the note? The product of any two numbers is equal to always the product of their LCM and HCF. Product of any two numbers is equal to LCM into HCF. Now let us take one more example. Find the LCM and HCF of 12, 5 and 21 by the prime factorization method. So we have 12 is equal to, I can write 2 into 2 into 3, which can be written as power form as 2 square into 3 power 1. And 15 I can write 3 into 5, the power form as 3 power 1 into 5 power 1. And 21 is equal to 3 into 7, which can be written as 3 power 1 into 7 power 1. Now for finding the LCM of 12, 15, 18, now I should list out all the prime factors. The prime factors which we are having is 2, 3, 5, 7. So now I list out all the primes here, 2, 3, 5, 7. Now go for the powers. So which power to be taken? For LCM, always the greatest power. So in the comparison, what is the 2 power greatest in here? 2 square is the greatest. So I am taking 2 power 2. And comparing for 3, in the 3 prime factorization, 1 is the only number which we are having. So I am writing 3 power as 1. And same way 5 power 1 and 7 power 1. Which can be written as 2 square is 4 into 3 into 5 into 7, which is 4 into 3 is 12, 12 5 is 60, 67 is 420, and 420 is LCM. Now coming to HCF, for HCF we should again check the 3 prime factorization, whatever common in all 3 terms, that will be our HCF. So what is the number which is common in all 3? Only 3 is the common in all 3, so I can take 3, and the 3 is having only one time, that is power is 1, 3 power 1 is equal to 3, which is my HCF. So LCM is equal to 420 and HCF is equal to 3. Now let us recall rational numbers and their decimal expansion, which we have learned in the previous classes. So what is a rational number? The number which is in the form of p by q, where q not 0 and p comma q are integers, is called rational number. The number which is in the form of p by q, where q not 0 and p comma q are integers, is called rational numbers. The decimal form of rational numbers is, there is a 2 forms, one is a terminating decimal and one is non-terminating recurring decimal. So decimal form of rational number is 2 forms, one is terminating decimal and non-terminating recurring decimal. So terminating decimal, example if you take 5.34, which is a terminating decimal, and non-terminating recurring decimal is 2.666 up to so on, which also can be written as 2.6 bar. Based on this, we are having 3 theorems. The first theorem is, let x be a rational number whose decimal form terminates. So there is a rational number x and their decimal form is terminating. Then x can be expressed in the form of p by q and q can be written in the form of 2 power n into 5 power m, where n comma m are positive integers. So this is the important theorem where we are telling us, let x be a rational number whose decimal form terminates, then x can be expressed in the form of p by q, where the q denominator can be written in the form of 2 power n into 5 power m. And the converse of this theorem is theorem number 2, which we can write as, let x be a rational number such that the prime factorization of q is of the form 2 power n into 5 power m. Then x has a decimal expansion which terminates. So this is the theorem 2 is the converse of theorem 1. Let x be a rational number such that the prime factorization of q is in the form of 2 power n into 5 power m. Then x has a decimal expansion which terminates. That means that will be a terminating decimal. Theorem 3, let x be a rational number such that the prime factorization of q is not in the form 2 power n into 5 power m. Then x has a decimal expansion which is non-terminating recurring. So we can conclude that terminating decimal, then denominator in the form of 2 power n into 5 power m. If denominator in the form of 2 power n into 5 power m, then it will be a terminating decimal. Non-terminating repeating decimal can be written as the denominator is not in the form of 2 power n into 5 power m, or else if denominator is not in the form of 2 power n into 5 power m, then the decimal form is non-terminating repeating decimal. Now let us recall irrational numbers. What is irrational number? A real number is called irrational if it cannot be written in the form of p by q, where q not 0 and p comma q are integers. A real number is called irrational if it cannot be written in the form of p by q, where q not 0 and p comma q are integers. Now let us see examples for irrational number. Root 2, root 3, root 5, root 6, root 7, root 8, root 10, root 11, root 12. So these are all the irrational numbers. Here we can note that root n is an irrational if n is not a perfect square. Also we can take third root of 2, third root of 3, all the thirds are irrational numbers only. And second type of example, 0.10, 110, 1110, 1111 up to so on is a one number, non-terminating non-repeating decimal, and 1.5347 up to so on is also non-terminating non-repeating decimal. So these are all non-terminating and non-repeating decimals are example for irrational number. And pi and e, and also log 2, log 3, etc. So you are going to learn about log 2, log 3 and e in the next class. Some properties of irrational numbers: let q be rational and s be irrational, and q is not 0, s is not 0. Then sum of q plus s is always irrational, q minus s is always irrational, product q into s is always irrational, quotient q divides s is always irrational. That means sum of rational irrational is always irrational, difference of rational and irrational is always irrational, product of rational and irrational is always irrational, and also quotient of rational and irrational is always irrational. Prove that root 3 plus root 5 is irrational number. So let us prove this by contradiction. So what is a contradiction? So irrational number opposite is a rational number. So let us take this proof by assuming given number as irrational. So let us assume that root 3 plus root 5 is rational. So the definition of rational number which we are having is, which will be in the form of p by q, where q is not integer. Let root 3 plus root 5 is equal to a by b, where a comma b integers and b not 0. Squaring on the both sides, then it will be root 3 plus root 5 whole square is equal to a by b whole square. So if you observe a plus b whole square formula here, a square plus b square plus 2ab. A square will be root 3 whole square is 3 and root 5 whole square is 5 plus 2ab, 2 into root 3 into root 5 will be root 15 is equal to RHS I can write as a square by b square. So here I am using the formula a plus b whole square. So 3 plus 5 is equal to 8 plus 2 root 15 is equal to a square by b square. Now if I send 8 to the right hand side, it will become 2 root 15 is equal to a square by b square minus 8. Here 2 root 15 is equal to, if I take b square as LCM, which can be written as a square minus 8b square. So 2 root 15 is equal to a square minus 8b square by b square, and 2 I am sending to right hand side, which will become root 15 is equal to a square minus 8b square by 2b square, which we will consider as equation number 1. Now if you observe, there is a LHS and RHS. LHS is root 15 and RHS we are having a square minus 8b square by 2b square. Since a comma b are integers, then a square minus 8b square by 2b square is a rational. So root 15 is also rational. Here we are getting RHS is a rational, then obviously the LHS also will become a rational number. So we are getting here root 15 is a rational number. This contradicts the fact that root 15 is irrational. We know that root 15 is a irrational number, which is a contradicting to the fact that root 15 is irrational. This has arisen because of our wrong assumption. What was our assumption? Our assumption was root 3 plus root 5 is rational number. While doing the process, we got root 15 is a rational, which is a contradicting to the fact that root 15 is a irrational. So why this has come? This has arisen because of our wrong assumption. So we can conclude that root 3 plus root 5 is irrational number. So this is the proof of a given number is a irrational number. Try yourself. Prove that root 3 plus 2 root 5 is irrational. And second problem, prove that root 3 plus root 5 is irrational. Prove that 3 minus root 5 is irrational. And prove that 3 plus 2 root 5 is irrational. So if you observe the 4 problems, first problem you always do the squaring on the both sides, and next 3 problems you need not to do the squaring on the both sides. Directly you can assume that whatever the number is given, suppose second problem 3 plus root 5 is equal to a by b, you assume it, then send 3 to right hand side, root 5 is equal to a by b minus 3, then do the process, you will get a contradictory, and this contradiction will arise based on the our assumption that given number as rational numbers. So this is the process of doing and process of proving an irrational number. For better understanding of the concept, solve the worksheets. Please visit the official website of SCRT for worksheets. Thank you for watching this video, and in the next class we are going to learn an interesting and important topic, logarithm. Thank you one and all.
భారతీయ పౌరుల ప్రాథమిక హక్కులు. భారత రాజ్యాంగం భారతదేశ పౌరులందరికీ కొన్ని ప్రాథమిక హక్కులు కల్పించింది. హక్కు అంటే అవకాశం, అధికారం కలిగి ఉండడం. ప్రాథమిక హక్కులు పౌరులకు తమ వ్యక్తిత్వాన్ని అభివృద్ధి పరుచుకున్నటకు, బాధ్యత కలిగిన పౌరులుగా హుందాగా జీవించుటకు, ప్రభుత్వ పరంగా చట్టరీత్యా ఇవ్వబడిన స్వేచ్ఛా స్వాతంత్రాలు అనుభవించుటకు కల్పించబడ్డాయి. భారత రాజ్యాంగంలో ఉన్న ప్రాథమిక హక్కులేంటో ఒకసారి చూద్దాం. సమానత్వపు హక్కు. సమానత్వపు హక్కు ప్రకారం చట్టం దృష్టిలో అందరూ సమానులే. వ్యక్తుల మధ్య కుల, మత, వర్ణ, ప్రాంత, లింగ, సంపద, విద్య వంటి విచక్షణలను ఈ హక్కు నిషేధిస్తుంది. ఈ హక్కు ప్రకారం రాజ్యాంగంలోని చట్టాలందరికీ ఒకే విధంగా వర్తిస్తాయి. స్వాతంత్ర్యపు హక్కు. భారత రాజ్యాంగం తన అధికరణలు 19, 20, 21, 22ల ద్వారా స్వాతంత్ర్యపు హక్కుని ఇస్తుంది. స్వాతంత్ర్యపు హక్కు 6 స్వేచ్ఛలకు హామీ ఇస్తుంది. వాక్ స్వాతంత్రం, భావ ప్రకటన స్వేచ్ఛ, ఆయుధాలు లేకుండా శాంతియుతంగా సమావేశమయ్యే హక్కు, సంఘాలుగా సభలుగా ఏర్పడే హక్కు, స్వేచ్ఛగా సంచరించే హక్కు, భారతదేశంలో ఎక్కడైనా నివసించడానికి స్థిరపడడానికి హక్కు, ఏ వృత్తి అయినా ఉపాధి, వాణిజ్యం, వ్యాపారమైన చేపట్టే హక్కు. మత స్వాతంత్ర్యపు హక్కు. భారతదేశంలో పౌరులందరికీ మత స్వాతంత్ర్యపు హక్కును అధికరణలు 25, 26, 27 మరియు 28ల ప్రకారం ఇవ్వబడింది. భారత రాజ్యాంగం ప్రకారం భారతదేశంలోని అన్ని మతాలు సమానమే. ఏ మతము ఇతర మతంపై ప్రాధాన్యతను కలిగి లేదు. ప్రతి పౌరుడు తన ఇష్టానుసారాన్ని మతాన్ని అవలంబించుటకు స్వేచ్ఛ కల్పింపబడ్డాడు. రాజ్యాంగ పరిహారపు హక్కు. భారత ప్రజలు తమ ప్రాథమిక హక్కులకు ఉల్లంఘన జరిగినప్పుడు రాష్ట్రాల ఉన్నత న్యాయస్థానాలను, సర్వోన్నత న్యాయస్థానాన్ని ఆశ్రయించే హక్కు ఉంది. న్యాయస్థానాలు ప్రత్యేక ఆదేశాలు జారీ చేయడం ద్వారా ఈ హక్కులను తిరిగి అందిస్తాయి. ప్రజల ప్రాథమిక హక్కులు ఉల్లంఘించబడకుండా చూడాల్సిన బాధ్యత ప్రభుత్వానికి. సాంస్కృతిక, విద్యా సంబంధమైన హక్కు. భారతదేశం అనేక మతాలకు, భాషలకు మరియు సంస్కృతులకు నిలయం. రాజ్యాంగం వీరికి కొన్ని ప్రత్యేక హక్కులను ఇస్తుంది. అధికరణ 29 మరియు 30ల ప్రకారం మైనారిటీలకు కొన్ని హక్కులు ఇవ్వబడినవి. మైనారిటీలు అనగా మతం, భాష మరియు సాంస్కృతిక పరమైన మైనారిటీలు. తమ మతాన్ని, భాషలను, సంస్కృతిని రక్షించుకొనుటకు మైనారిటీ సంస్థలు స్థాపించుకోవచ్చును. ఆ సంస్థల ద్వారా వారు తమ అభ్యున్నతికి పాటుపడవచ్చును. దోపిడీని నిరోధించే హక్కు. అధికరణలు 23 మరియు 24 ప్రకారం కట్టు బానిసత్వం మరియు బాలకార్మికుల విధానాలు నిషేధం. మరియు 14 సంవత్సరాలలోపు బాలబాలికలతో అపాయకరమైన పనులు అంటే కర్మాగారాల్లో, గనుల్లో పని చేయించుట నిషేధం.